this video, we'll look at a couple of quick points about the fundamental theorem of calculus. First of all, we've talked about definite integrals for a while now. One of the things you can do with definite integrals is look at limits of integration that go in the opposite direction. So a regular definite integral from a to b of f of x dx, is the opposite of the definite integral from b to a of f of x dx. And if we look at an example of this, it does seem a little bit weird to even talk about the definite integral from b to a. So I'm going to label these points a, b, and we'll do this one c also. So the definite integral from a to b definite integral from a to b of f of x dx, let me call this function f of x, is, we've talked about this a bunch, the definite integral is the product of this y value times the x distance, or the changing y value times the x distance. And so it makes sense that the definite integral from a to b is going to end up being the area of this whole curve. Let's just say this area was 5. Okay. The point is, what connects to the property I wrote above is if I were to take the definite integral from b to a, the definite integral from b to a of f of x dx, it's a very similar idea. The big difference is going to be that still it's the product of a y value times an x distance, but now the y value, it's the same y value up here, that's f of x, but dx, if I'm going from b to a, that dx is actually going in this direction, it's backwards, so it's a negative number. So it's a positive y value times a negative number, so it makes sense that it's the opposite of the definite integral from a to b of f of x dx. Also worth pointing out while we're here that in this case the definite integral from b to c of f of x dx, let's say that this is a symmetric graph, so the area here is also 5. But since the definite integral is multiplying a y value times an x distance, the y value is negative, the x distance is positive. When you multiply those two things together, you will get a negative 5, the definite integral from b to c of f of x dx. On the other hand, the definite integral from c to b of f of x dx would be taking two negative numbers, the negative y value times the negative x distance. Well, that'll work itself out to be a positive 5. One other thing I want to show you about definite integrals and how we can use the fundamental theorem. We can, if we're given information about a rate of change, that's what this is. We're given the graph of the rate of change, f prime of x. We can use that to figure out how much f itself has changed. And so if we're told one particular value of f, we can use the change in f combined with that one piece of information about f to plot a lot of other points for f2. Let me show you what I mean, because that didn't make a whole lot of sense the way I said it. The definite integral from a to b of any function, I'm going to use the function f prime of x, is equal to the antiderivative of that function, which in this case is regular f, evaluated at b, minus the antiderivative of that integrand evaluated at a. That's the fundamental theorem. When we said it in class the other day, we happened to have used f of x as the integrand, which meant we used capital F as its antiderivative. Where'd it go? Let me catch up to what I just wrote. The definite integral from a to b of f prime of x dx is equal to f of b minus f of a, which, like I was saying, is the same thing as what we described as the general fundamental theorem, which is the definite integral of regular f of x dx is equal to the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. These are two ways of saying the same thing. The reason why this is useful to us is because if we are given information about f prime, like we're given its graph, we could figure out the definite integral using the area under the curve. So if we want to figure out, let's say, f of 5, we could say that the definite integral from 3 to 5 of the rate of change of x, f prime of x, in respect to x, is the same thing as the total change in f. So that's f of 5 minus f of 3 between those two x values, 3 and 5. Well, the reason why this is helpful is because we know through two of those three things. We know that f of 3 is 7, and we can figure out the definite integral from 3 to 5 of f prime of x dx by using the area of that triangle. So the definite integral from 3 to 5 of f prime of x dx is negative 2. We're trying to find f of 5, and we know that f of 3 is 7. So using all this, we can solve for f of 5, say that f of 5 equals 5, which means that the graph of f will pass through there. We can do the same thing for any other point on the curve. For example, if I wanted to find f of negative 1, I could say the definite integral from negative 1 to 3 of f prime of x dx, I'm going to draw a line here to show that I'm doing something different, is equal to f of 3 minus f of negative 1. And we can figure out the antiderivative of, the definite integral from negative 1 to 3 of f prime of x dx would be the area here. All of that, so the area of that triangle would be this definite integral. Well, that is a triangle with a base of 4 and a height of 4, so that is 1/2 4 times 4, which is 8, equals f of 3 minus f of negative 1, which we don't know yet, but we can find it out just by solving. F of negative 1 must be negative 1. So I can plot the point negative 1 comma negative 1. And that's really all I really need in here. I can use a couple of other points. Remember what we've said several times is that when a derivative is linear, the function that it is the derivative of must be quadratic. When a derivative is 0, that means it's that spot on the original function must have a horizontal tangent, which means that point 3,7 isn't just any point, it's the vertex of a parabola, which means there's symmetry. So if we know f of 5 is equal to 5, that means f of 1 must be equal to 5 also, because of symmetry. So that's really enough to do a pretty good job of connecting those points. And we also know, because everything from 5 on, f prime is constant, which means f is linear with a slope of 1, so we can just draw that line with a slope of 1. And that's a pretty good sketch of f of x.